Welcome to the quantum world, a realm far stranger than science fiction. Here, the familiar rules of physics crumble, replaced by a captivating dance of probability and uncertainty. Quantum mechanics, at its heart, is the study of the very, very small atoms and the particles within them. These tiny entities behave in ways that defy our everyday intuition, challenging our understanding of reality itself. Imagine a world where objects can be in multiple places at once, where information travels instantaneously across vast distances, and where the act of observation alters the very fabric of existence. This is the captivating realm of quantum mechanics, a field teeming with wonder, mystery, and mind-boggling implications that continue to reshape our world. Everything around us, from the air we breathe to the stars in the night sky, is composed of atoms. These minuscule particles are the fundamental building blocks of matter, the smallest units that retain the chemical properties of an element. Imagine an atom as a miniature solar system. At its center resides the nucleus, a dense core comprising positively charged protons and neutral neutrons. Whizzing around the nucleus are electrons, negatively charged particles, much like planets orbiting a star. These electrons, however, don't follow fixed paths like planets. Instead, they exist in blurry clouds of probability, their exact location and momentum uncertain. This inherent fuzziness is a hallmark of the quantum world. The quantum world is a realm of perplexing paradoxes and counterintuitive phenomena. Here, particles can exist in multiple states at once, a concept known as superposition. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. Similarly, a quantum particle exists in a blend of all possible states until measured. Even more bizarre is entanglement, where two particles become linked, their fates intertwined regardless of distance. If you measure the state of one entangled particle, you instantly know the state of the other, even if they're light years apart. This spooky action at a distance, as Einstein famously called it, seems to defy the limits of speed and locality, hinting at a deeper interconnectedness within the fabric of reality. In the quantum realm, certainty gives way to chance. We cannot predict the exact behavior of a quantum particle with absolute precision. Instead, we deal with probabilities. Imagine a single photon of light hitting a half-silvered mirror. Classical physics would suggest it either passes through or reflects. Quantum mechanics, however, dictates a 50-50 chance for either outcome. This inherent randomness is not due to a lack of information, but rather a fundamental aspect of the quantum world. It's like rolling a cosmic dice, where the outcome is governed by probabilities rather than predetermined certainty. This probabilistic nature of quantum mechanics has profound implications for our understanding of reality, suggesting that at the most fundamental level, the universe is inherently uncertain. Section 5, Duality, the wave-particle mystery. One of the most mind-bending concepts in quantum mechanics is wave-particle duality. This idea has puzzled scientists and philosophers alike for decades. This principle states that quantum entities, like light and electrons, can exhibit properties of both waves and particles, depending on how they're observed. It's a fundamental aspect of quantum theory that defies our everyday experiences. Imagine a beam of light passing through two slits. This classic experiment, known as the double-slit experiment, is a cornerstone in understanding wave-particle duality. Instead of creating two distinct lines on a screen behind, it produces an interference pattern, characteristic of waves. This pattern is a series of light and dark bands, showing the wave nature of light. Yet, light can also behave like a stream of particles, carrying energy in discrete packets called photons. These photons can be counted individually, demonstrating the particle aspect of light. This dual nature of matter and energy challenges our classical intuition, blurring the lines between what we perceive as waves and particles. It forces us to rethink the very nature of reality. It's as if nature is playing a cosmic game of hide and seek, revealing its true nature only when we're not looking directly. This enigmatic behavior is at the heart of quantum mechanics, making it one of the most fascinating fields of study in modern science. Section 6. Entanglement. Spooky action at a distance. Entanglement is one of the most baffling and intriguing phenomena in quantum mechanics. It describes a bizarre connection between two particles where their fates are intertwined regardless of the distance separating them. Imagine two coins flipped simultaneously, one landing on heads, the other on tails. In the quantum world, these coins could be entangled. If you were to observe one coin and find it heads, you'd instantly know the other is tails, even if they were light years apart. This instantaneous correlation between entangled particles, dubbed spooky action at a distance by Einstein, seems to defy the limits of speed and locality. It suggests a deeper, more profound connection between quantum entities than anything we experience in the classical world. Section 7F, fuzzy not fixed, the uncertainty principle. One of the cornerstones of quantum mechanics is Heisenberg's uncertainty principle, a concept that fundamentally challenges our classical understanding of the universe. This principle states that we can never simultaneously know both the position and momentum of a quantum particle with perfect accuracy. The more we try to pin down one, the more the other eludes us. Imagine trying to pinpoint the exact location and speed of a buzzing fly. It's a bit like trying to catch smoke with your bare hands. The more precisely you measure its position, the less you know about its speed, and vice versa. This trade-off is a fundamental aspect of the quantum world. This inherent uncertainty is not due to limitations in our measuring tools, but rather a fundamental property of nature itself. It's as if the universe has built-in fuzziness at its most basic level. The very act of observing a quantum system inevitably disturbs it, introducing a degree of fuzziness into our measurements. This disturbance is unavoidable and intrinsic to the nature of quantum mechanics. The uncertainty principle has profound implications for our understanding of reality, suggesting that at the quantum level, nature itself is inherently uncertain and probabilistic. This means that the universe operates on probabilities rather than certainties, reshaping our perception of what is real and what is possible. Section 8G, Gravitational Mystery. While quantum mechanics has revolutionized our understanding of the very small, it faces a significant challenge, reconciling with Einstein's theory of general relativity, which governs the very large, gravity. Imagine trying to fit a square peg into a round hole. Quantum mechanics and general relativity, while incredibly successful in their respective domains, seem fundamentally incompatible when it comes to describing gravity at the quantum level. This incompatibility has puzzled physicists for decades, leading to a quest for a unified theory of quantum gravity. A theory that could bridge the gap between the quantum realm and the cosmos, explaining phenomena like black holes and the Big Bang. Section 9H, How Quantum Mechanics Shapes Our World. Despite its strangeness, quantum mechanics is not just an abstract theory confined to the realm of physics labs. It underpins many technologies we use daily, shaping our modern world in profound ways. Lasers, transistors, and magnetic resonance imaging, or MRI, all rely on the principles of quantum mechanics. These technologies have revolutionized communication, computation, and medicine, illustrating the practical impact of this seemingly bizarre theory. Moreover, quantum mechanics is paving the way for future technologies, such as quantum computers and quantum cryptography, which promise to revolutionize fields like medicine, materials, science, and artificial intelligence. The quantum revolution has only just begun, and its impact on our lives is bound to grow exponentially in the coming decades. Section 10I, Implications for the Future. Quantum mechanics continues to challenge our understanding of the universe, raising profound philosophical questions about the nature of reality, causality, and the role of the observer. These questions are not just academic. They have real-world implications that could transform technology, communication, and even our daily lives. As we delve deeper into the quantum realm, we're bound to encounter even more mind-boggling phenomena, pushing the boundaries of our imagination and challenging the very foundations of our scientific worldview. The discoveries we make could lead to revolutionary advancements in computing, cryptography, and materials science, opening up possibilities we can scarcely imagine today. The quest to unravel the mysteries of quantum mechanics is far from over. Each new discovery brings with it a host of new questions, driving scientists to explore further and deeper into the unknown. It's a journey into the heart of reality, promising to reshape our understanding of the universe and our place within it for generations to come. The implications of these discoveries extend beyond science, influencing philosophy, ethics, and even our perception of existence itself. The future of science, like the quantum world itself, is uncertain, but one thing is clear. It's bound to be filled with wonder, discovery, and a profound sense of awe at the sheer strangeness of it all. As we stand on the brink of these new frontiers, we are reminded that the pursuit of knowledge is an endless journey, one that continually reshapes our understanding and appreciation of the cosmos.